Here we see a similar curve supposed to represent the same curve, but it got a little bit lopsided. Some v equals at squared plus bt plus c curve. Let's assume that it's over the same time interval, over t equals 0 to t equals 9 as the previous, but we've divided the curve into a larger number of trapezoids, maybe 4 times as many trapezoids as we had before. The many trapezoids that we have are going to stay much closer to the curve. We have 4 times as many trapezoids. I'd venture to say that we're much better than 4 times closer to the curve. We're almost right on this curve. There's almost no deviation here. Now, we can think about what this means. In the first place, our accumulated area from here to any point will be much more accurate. So we can come much closer to determining the total amount of position change, of course, because the areas under the curve represent position changes. The total position change between any 2 points, since we have a much finer grain, a much finer mesh to this division of trapezoids, we can get much better information between 2 points that don't happen to lie right at the end of 2 trapezoids that we've constructed. Also, our slopes. If we have the exact slope at one point, remember we can find the exact slope of such a function here. It's going to be 2at plus b. So we take any point down here that's not at the end of one of the trapezoids, not necessarily in the middle, just any point within one of the trapezoids. The slope at that point is going to be very close to the slope of the trapezoid because there's not much change in slope over the width of one of these small trapezoids. In other words, the curve is approximately a straight line over each trapezoid. As we let the delta t approach 0, our approximations become exact. And if, by symbolic calculations, we can get an expression for the slope function as we can for this quadratic function, or an expression for the accumulated area function, we can find either the exact slope at a point which will better and better match the slope that's given over the corresponding trapezoid as the trapezoids get smaller, and we can find the difference in position between any 2 points corresponding to the area under the curve between those 2 points. And that approximation again approaches exactness as the delta t approaches 0. Just a word on the word integral. We integrate many small areas into the total area. To integrate is to make one, to sum many small things into one, or in some way to bring things into a whole. We bring all these areas into one, even as delta t goes to 0, and if we can devise a technique for doing that, and for doing that symbolically so that we can get an expression for the integral of this function, we can determine exact areas, and we have what's called an exact integral.